Today we are going to learn about demystifying AUC, beyond basic concepts. We will explore advanced concepts of AUC, equipping you with the skills to interpret AUC results and apply them in practical scenarios. Welcome to our educational series on demystifying AUC, beyond basic concepts. In this video, we will delve into the advanced aspects of the area under the curve, commonly known as AUC, which is a pivotal metric in assessing the performance of classifiers in data science. Throughout this session, we aim to equip you with not just the theoretical understanding of AUC, but also practical skills on how to interpret and apply AUC results in real-world scenarios. By the end of this video, you will have a comprehensive understanding of why AUC is often a preferred metric over accuracy, how to interpret different AUC values, and the limitations and challenges associated with its use, particularly in balanced datasets. We'll also compare AUC to other performance metrics, explore case studies, and introduce you to tools and libraries for calculating AUC in Python. So, let's begin our journey into demystifying AUC.
Let's start by defining AUC in the context of classifier performance. AUC stands for area under the curve, specifically the receiver operating characteristic, ROC, curve. The ROC curve is a graphical representation that illustrates the diagnostic ability of a binary classifier system as its discrimination threshold is varied. Mathematically, AUC is the area under the ROC curve, providing a single scalar value representing the classifier's ability to distinguish between classes. The ROC curve plots the true positive rate, TPR, against the false positive rate, FPR, at various threshold settings. The true positive rate, also known as sensitivity, measures the proportion of actual positives correctly identified, while the false positive rate measures the proportion of negatives incorrectly classified as positives. Calculating AUC involves integrating the area under the ROC curve, which can be done using numerical methods such as the trapezoidal rule. The AUC value ranges from 0 to 1, where a value of 0.5 indicates no discrimination, equivalent to random guessing, and a value of 1 indicates perfect discrimination. Understanding the mathematical foundation of AUC is crucial as it forms the basis for interpreting its results and applying it in various data science tasks.
One of the core reasons AUC is often preferred over accuracy in evaluating classifier performance is its ability to account for class imbalance. Accuracy, defined as the number of correct predictions over the total number of predictions, can be misleading in datasets with unequal class distributions. For instance, in a dataset where 90% of the instances belong to one class, a model that always predicts the majority class will achieve 90% accuracy, which might seem excellent but is actually trivial. In contrast, AUC provides a more nuanced picture by considering the trade-off between true positive and false positive rates across different thresholds, making it threshold independent. This independence from a specific threshold allows AUC to offer a comprehensive measure of a model's performance across all classification thresholds, providing insight into the model's ability to distinguish between classes. Furthermore, AUC is less affected by class imbalance, making it suitable for real-world applications where imbalanced datasets are common. By understanding these advantages, data scientists can make informed decisions on model evaluation and selection, particularly in scenarios where accuracy alone may not suffice to capture the model's true performance. Interpreting AUC values is essential for assessing the effectiveness of a classifier. An AUC value ranges from 0 to 1, where 0.5 indicates a model with no discrimination ability, equivalent to random guessing. Typically, an AUC over 0.7 is considered acceptable, over 0.8 is considered excellent, and over 0.9 is considered outstanding. However, what constitutes a good AUC can vary depending on the context and the specific application. For example, in medical diagnostics, where the cost of false negatives is high, a higher AUC might be necessary to ensure the model's reliability. Conversely, in other applications, a slightly lower AUC might be acceptable if the model is efficient and cost-effective. It's important to consider the domain-specific requirements and constraints when interpreting AUC values. Furthermore, it's crucial to ensure that the AUC is calculated and interpreted correctly, considering factors such as the choice of positive and negative classes and the impact of any pre-processing steps. By understanding these nuances, practitioners can make informed judgments about model performance and suitability for specific tasks. While AUC is a powerful metric, it's important to be aware of its limitations and considerations. One limitation is that AUC may not always be reliable in highly imbalanced datasets, where the number of instances in one class significantly outweighs the other. In such cases, AUC might provide an overly optimistic view of the model's performance. Additionally, although AUC is threshold independent, the ROC curve does not provide information about the optimal threshold for classification, which may be crucial for decision-making in certain applications. It's also possible for different models to have the same AUC but different underlying performance characteristics, leading to potentially misleading interpretations. To mitigate these issues, It's advisable to use AUC in conjunction with other metrics, such as precision, recall, and F1 score, to gain a more comprehensive understanding of model performance. Moreover, practitioners should consider domain-specific requirements and consult with domain experts to ensure that the chosen metrics align with the application's goals. By recognizing the limitations and considerations when using AUC, data scientists can make more informed decisions and avoid potential pitfalls in model evaluation.
Imbalanced datasets, where one class significantly outnumbers the other, pose unique challenges in model evaluation, and AUC is no exception. In such scenarios, AUC can sometimes give an overly optimistic assessment of a model's performance, as it may not adequately reflect the model's ability to correctly classify the minority class. To address these challenges, several techniques can be employed. One approach is resampling methods, such as oversampling the minority class or undersampling the majority class, to create a more balanced dataset. Another technique involves using synthetic data generation methods, like synthetic minority oversampling technique, SMOTE, to create new instances for the minority class. Additionally, cost-sensitive learning can be employed, where different misclassification costs are assigned to different classes, allowing the model to focus more on correctly classifying the minority class. It's essential to evaluate models using a combination of metrics, including precision, recall, and F1 score, to complement AUC and provide a more comprehensive view of performance. By understanding the challenges of imbalanced datasets and applying appropriate solutions, practitioners can more accurately assess model performance and make informed decisions in real-world applications. AUC is a valuable metric, but it's often used in conjunction with other performance metrics to provide a more comprehensive evaluation of a model's performance. While AUC measures a model's ability to distinguish between classes, it does not provide information about the precision or recall of the model. Precision, defined as the number of true positive predictions divided by the total number of positive predictions, measures the model's ability to avoid false positives. Recall, on the other hand, measures the model's ability to identify all relevant instances, defined as the number of true positive predictions divided by the total number of actual positives. The F1 score, a harmonic mean of precision and recall, provides a single metric that balances both precision and recall, particularly useful in imbalanced datasets. It's crucial to choose the appropriate metric based on the specific application and its requirements. For instance, in applications where false positives are costly, precision may be prioritized, while in scenarios where false negatives are critical, recall may be more important. By comparing AUC to other metrics and understanding their respective strengths and weaknesses, practitioners can make more informed decisions about model evaluation and selection.
To illustrate the practical applications of AUC, let's explore some real-world case studies where AUC played a crucial role in model evaluation and decision-making. In the healthcare industry, AUC is often used to evaluate predictive models for diagnosing diseases, where accurately distinguishing between healthy and diseased patients is paramount. For example, a study evaluating a machine learning model for early cancer detection used AUC to assess the model's discrimination ability, guiding improvements in the diagnostic process. In the finance sector, AUC is employed to evaluate credit scoring models, where distinguishing between creditworthy and non-creditworthy applicants is essential for risk management. A case study involving a bank's credit scoring system found that incorporating AUC alongside other metrics helped identify areas for model refinement, ultimately improving the system's accuracy and efficiency. These case studies demonstrate the importance of AUC in real-world applications, highlighting its role in guiding model evaluation and refinement. By learning from these examples, practitioners can apply similar strategies in their own domains, leveraging AUC to enhance model performance and achieve better outcomes.
Python is a popular programming language in data science, and several libraries offer tools for calculating AUC efficiently. One of the most widely used libraries is Scikit-learn, which provides a comprehensive suite of tools for machine learning and model evaluation. Scikit-learn's rock_awk_score function allows for easy calculation of AUC by taking true labels and predicted probabilities as inputs. Additionally, the library offers functions for plotting ROC curves, enabling visual evaluation of model performance. To implement AUC calculation in Python, users can follow these steps. First, import the necessary libraries, such as Scikit-learn and matplotlib for visualization. Then, train your classifier and obtain predicted probabilities or decision function scores. Finally, use the rock_awk_score function to calculate the AUC and plot the ROC curve using matplotlib. It's important to ensure that the input data is properly formatted and preprocessed, as this can affect the accuracy of the results. By utilizing these tools and libraries, practitioners can efficiently calculate AUC, visualize model performance, and integrate the results into broader data science workflows. Understanding these practical aspects of AUC calculation equips data scientists with the skills needed to apply AUC effectively in their projects.
In conclusion, we've explored the advanced concepts of AUC, delving into its mathematical foundation, advantages over accuracy, and interpretation of values. We've discussed the limitations and considerations when using AUC, particularly in imbalanced datasets, and compared it to other performance metrics. Through real-world case studies, we've seen the practical applications of AUC in guiding model evaluation and decision-making. Finally, we've introduced tools and libraries for calculating AUC in Python, providing practical insights for implementation. As you continue your journey in data science, we encourage you to explore these concepts further and apply them in your projects, leveraging AUC to enhance model performance and achieve meaningful outcomes. Thank you for joining us in Demystifying AUC, and we look forward to seeing how you apply these insights in your work.